class. Guess what? It's time for some linear correlation, which is chapter 9.6. Let's go ahead and turn this over right there. So pre-calc, linear correlation, chapter 9.6. Let's go ahead and look at page 474. And I want you to look at this data really quickly. So if you were to look here, this point right there, right, that's one of the data points. That's another data point here in purple. These are all the data points that they gave us in the book. And when you look at those, if you were to plot them on the graph like I did, you notice that if you were to add them all up and do this, take the average, right, add them all up and divide by how many there are, that you would take all the data, add them all up, divide by how many are, you get 3.29. That's the average. We're going to call that y bar instead of x bar because we're dealing with the heights, the y. So if you notice, I got my y bar here at 3.29. I drew a little pencil mark all the way across, and that would be my average. But the data doesn't fit that very well because like this data is way below it, this data is below. These are above, but none of them are actually near the average. So it's kind of like, well, that data doesn't look very good. So it would be better to get what's called a line of best fit, which is to have something that goes really close to the data. So let's go look at that. So this line of best fit would be this orange line that goes right through it. And that would be a better representation than the average, right? The average is just an average, but it's not a very well-fitting average. So what I did is I call this thing over here y hat. You'll see that in the book. Y hat. So y hat, like y sub I, just meaning an individual y. Y hat is the predicted value on the line of best fit. So y hat's drawn here in black. So if we go up here, the y hat value would be the more accurate value where the data would be best if I were to make it the line of best fit, or if I were to find all of the averages and kind of squish them towards that line, that would be my y hat. So y hat is a better, for a better line of best fit than my actual average. So let's go, keep on going. So what I'm going to do is I'm going to create that line of best fit here. This is what this orange line of best fit is right there. That orange line of best fit is the equation. This is my y hat equation, is to take the slope of my n times my individual x, the one that I plugged in, plus my b. So this is the line of best fit for the and the above, the average line of best fit right there. That is a really good average. And what we're going to do is we're going to define some terms here. So SSE, which is going to be the sum of the squared errors, right? Because there's an error each time. So that red, you can see there, I'll go really close. That red line, that's error, right? And then that's an error. And that's an error, right? And so what we're going to do is if I were to take the error here and the error there, like this might be a negative error and a positive error. And so what we want to do is we want to square them. So we're going to square our errors. And when we do that, the sum of the squared errors, that's what this is. The sum of the squared errors is finding the difference between the individual y, that the actual value, and the y hat, which is the predicted value. Let's go back over here. Are you guys still with me? Are you with me? Okay. So this value right here is the actual value. That'd be like your y sub 1. And then this is the predicted of where I actually wish it was. That'd be my y hat. So go over here. If I find the difference between my actual value and my y hat and I square it, it will always be positive. So then that turns into a positive. That turns into a positive because I'm squaring them all. But we also know that y hat, we defined y hat down here as this. So I can just plug it in. So if I just plug that value in, I get this. And if I distribute that negative, I get that. So this is the sum of the squared errors, and this is the equation that we're going to be using, the sum of the squared errors. So the sum of the squared errors represents the sum of the squared error. It's the error between the line of best fit and the actual data. Okay? So we can kind of apply that to a few things here. So SSX, okay, that's the differences of the actual x's and the average x's. So this is just the definition. If you square them and add them all up, that's the sum of the squares with x's. But that's going to always be positive. SSY is the sum of the squares of just the y values, right? And so you take the actual y, you subtract off the average y, you square them. That's going to have to be positive too when you add these all up. But the sum of the squares of x's and y's, this is the definition for that, is to find the difference between the actual x and the average, and the actual y and the average. And when you multiply those together, this could be positive or negative because we're not squaring it, if you notice. All right, on to the next thing. Okay, I think it's time for some example number 1 on page 475. Let's go ahead and take a look. Now, page 475, linear regression theorem, they give this to us. They say the definition of a linear regression is that we have to have y equals mx plus b. That's our line. Remember, if we went back, we're talking about our line here in orange. And if I want the equation of that, Page 475 there tells us that the equation is my slope is my SSXY over my SSX. My B value, my Y-intercept, is the average Y minus the slope times the average X. So on example number 1, on page 476 now, I go back to the original data that they gave me, right? This is the data on the first part of the page when we first started the chapter. Okay, keep on going. So this data that they gave us that I graphed right there, okay? We take that data, all my X's and all my Y's, and I found all of the information I needed here. So I did it, okay? So the average X, so if I add up all of the individual X's that I got, all of these here, if I add them all up and I divided by the 7 of them, all right, I get that there's going to be an average of 4. So my X bar is 4. My Y bar, same thing. You add up all your Y's, divide by 7. Your Y bar, your average Y is 3.29. We already got that. And then we have SSX, and that's the difference between here the initial X value and the average X value. Okay, if you take all of those, you square them, and you do that to all 7 data points, we know that our X bar is 4. So when you put that in there, you're going to end up adding them all up, and you end up with 28. Okay, our SSY is doing the same thing, but we're taking the difference between our individual Y value and our average Y value. And you're going to square all those, add them all up, square them. We know our average is a 3.29 from up there. So therefore, when you do all that, you're going to get 13.43 is your SSY. You do the same thing down here for your SSXY, right? The definition there was to find the difference between the X value that you had there and its average, and the Y value and its average. Multiply those together, all 7 data points, and you're going to get 17. So, are you sticking with me? I know this is a lot of stuff. You can always go back. You can rewind this and look at it again, but you've got to make sure you have these things memorized. Okay, you're doing great. So, if that's the case, then the slope, which we found here, the slope is just the SSXY divided by SSX. When I do that, it's the 17 divided by the 28, and I get 0.61. That's my slope. So that's going to be the slope of this line, the steepness of that line. Then, how do I find the Y-intercept, my B value? Well, this definition of my Y-intercept right here was that's the difference between my average Y and the slope times my average X. So now that I have my average Y, I got that up here, 3.29, minus the slope I just got here, 0.61, and the average X I got up here as a regular 4. Okay, if I put all that stuff in, I find out that my Y-intercept is 0.86. So that comes over here. It says when this comes down here, you're going to hit here at 0.86 at the Y-intercept. So, put all that stuff together. You got Y equals mx plus b. My slope is 0.61. My Y-intercept is 0.86. And so I've got my line of best fit. That is the equation of this line of best fit right there. Oh, it's absolutely gorgeous. But the thing they asked us on this question was on example number 1 on page 476 was, well, what happens in the 8th generation of this population of bacteria or whatever they're dealing with, right? So in generation 1, that was the population. Generation 2, that was the population. But what happens in the 8th? I don't have an 8th. I got to go find it. So find the 8th generation, you plug in the number 8, right? F of 8. Or go back down to this one, plug in 8 right there for your X. And when you do that, you're going to get 5.71. That tells us that if you go back over here and you would go all the way up here, and you're going to go 8th generation, and you're going to go all the way up, you'd hit about 5.71. Are you guys tracking with me? Hang in there. We're almost done. Okay, so how accurate is our data? That's the question. Is it correlated? Is it a good model? Let's find out. Remember, if we go back to this data, the question is this best fit line accurate comparatively to the average? Like the average we took, not very accurate. How much better is that best fit line? So how accurate is our line of best fit? And is this data correlated? So the correlation formula is to take your SSXY and divide it by the square root of SSX and SSY. When you do that, you're going to get your correlation. And if you square that number, R squared, take R and you square it, right? If you square that correlation, that represents the reduction of error over using the average. So how much better is this line of best fit comparatively to that pencil average of that 3.29, right? That's the question. So let's look at it. If your R squared happens to be near 0, okay, then it's worthless. You may as well throw the model out. It's not any better than just taking the average. You may as well just use the average because that's not anywhere, it's no good, not any percentage better. If your R squared is closer to 1, like 100% perfectly, that's going to be having no error at all. And all the data is sitting exactly on the best fit line, which would be perfect. If all of my data was all squished up onto the line, right, squished on the line, and I had all my data already on there, then it would be perfect model, and I would obviously want to use it. So the question then is, what is it? Let's look. Example number 2, page 477. You find your R value by plugging in the values here, numbers that we gave you, and you find out that the correlation is 0.88. Well, then what's the R squared? The R squared is to square that 0.88. That's 0.77 or 77%. What that means is that our model, our best fit line, was 77% better than using our Y bar, right? Our average. So it's 77% better. This line is, I just got, a bug just went up my nose. Okay. So this line right here, this best fit line, is 77% better than using the average right there. And there you have it, my friends. Land it out.